Welcome students to the presentation on dynamics, motion of a rigid body about a fixed axis.
First, you should be familiar with the moment of inertia. A moment of inertia is nothing but a measure of resistance of a body, and it is called also rotational inertia, and it is a resistance of a body to angular acceleration about a given axis, and it is equal to the sum of products of masses and the square of the perpendicular distance from the axis. You can see some examples: a bus moving from rest and stopping a ball, and also here you can see a glass of water closed with the cardboard, and there is a coin kept on the cardboard. Now if you pull the cardboard, then the coin, it falls into the glass. This is due to the inertia of the coin, and it falls inside due to the gravity. Now if m is the mass of a particle, then if r is the perpendicular distance from the given line, then moment of inertia is given by the expression mass into square of the distance, perpendicular distance. So m r square. If you consider a system with so many masses m1, m2, etc., and arranged at the points with the perpendicular distances r1, r2, etc., then the moment of inertia of the whole system is m1 r1 square plus m2 r2 square plus etc. So in general, if we can denote this by the expression capital M k square, and we call the k as the radius of gyration of the body above the line. And there is an important theorem which is called the theorem of parallel axis, and this theorem states that moment of inertia of a body about any axis is equal to the sum of moment of inertia about the axis parallel to the center of gravity, and we denote it by I suffix g, plus mh square, where m is the mass and h is the distance between two parallel axes. And also moment of inertia of some special cases, moment of inertia of a uniform rod about the line which is perpendicular to the line AB, and suppose the length is 2a, then the moment of inertia is given by the expression 4ma square by 3. And also moment of inertia of AB about itself will be equal to 0.
And these are the basic things you have to know. Now we can go into the topic, that is motion of a rigid body about a fixed axis. Now suppose m is the body, m is the mass of the body, and it rotates about the fixed axis through a point O perpendicular to the plane. Now let P be the particle, some particle in the above plane section, and the angle OQ makes an angle pi with a OX. So the angle QOX is equal to pi, and the angle POX is equal to theta. Now this angle POQ is equal to pi minus theta. And for a rigid body, this angle pi minus theta will be a constant value. And we know already we have know this. Angular velocity is theta dot, and it is given by the expression d theta by dt, and that is also equal to d pi by dt. And angular acceleration is theta double dot, that is d square pi by dt square, and that is equal to d square theta by dt square. So these expressions are common to all the points in the. Now we can find an expression for kinetic energy of a rigid body rotating about a fixed axis, and these are the notations we use. Omega is the angular velocity, capital M is the mass of the whole body, I is the moment of inertia, and P is the particle of mass small m, and distance r from the axis of rotation, that is the perpendicular distance. And now the linear velocity in a circle of radius r is given by radius into angular velocity, that is r into omega. So the kinetic energy of mass m at the point P at the particle P is equal to half m velocity square, that is r square omega square. Now the total kinetic energy is equal to half summation of half m r square omega square. Omega square is constant, so that you can take it out. So this is equal to half omega square summation m r square. And summation m r square is nothing but the moment of inertia. So we can replace this by capital I, half I omega square. And already we have an expression for kinetic energy of particle of mass m with the velocity v, that is half m v square. Now you see the equation 1 and 2. Here I takes the place of m and omega takes the place of v. That is the moment of inertia I and angular velocity omega, it takes the place of mass and the linear velocity v in translatory motion. So this motion is called translatory motion. And suppose if k is the radius of gyration of the body, then the moment of inertia I is equal to mk square, where m is the mass of the body. So the kinetic energy of a body is equal to half mk square omega square. Now we can see the angular momentum of a rigid body about an axis of rotation. And already we know that velocity of m is r omega and it is perpendicular to OP. Now the linear momentum is equal to mass into velocity, that is m into r omega, and moment is given by the formula linear momentum into radius, that is m r omega into r. So this is equal to m r square omega. Now sum of momenta of particles of body is equal to summation m r square omega, and since omega is constant we can take it out. So this is equal to omega sigma m r square, and sigma m r square is equal to I. So this is equal to I omega. So we get an expression for angular momentum, and that is equal to I omega. Again we can replace I by m k square omega. Next we will see the motion of a rigid body about axis of rotation. Now theta dot is the angular velocity and theta double dot is the angular acceleration for a rigid body. Suppose a mass m at P, it moves in a circle. Its component of accelerations are r theta dot square and r theta double dot. So there are two components of accelerations. Along the direction PO is r theta dot square, and perpendicular to the PO r theta double dot. And similarly there are two components of forces also. We know that force is equal to mass into acceleration. Therefore the two forces are m r theta dot square and m r theta double dot. These two forces are called effective forces. And see this component m or theta dot square, the direction of this component will be along PO and it also passes through O. And hence the moment about this axis is 0. Therefore this force, moment of this force becomes 0. Now a moment of the second force m or theta double dot is equal to m or theta double dot into radius. Therefore, that is equal to m r square theta dot. Now, sum of moments of effective forces, all the effective forces is equal to summation m r square theta double dot. And theta double dot is constant. Therefore, theta double dot into summation m r square, and summation m r square is nothing but the moment of inertia I. So, this is equal to I theta double dot. Now, there are two forces. One is the external force and other one is internal force. So, from A and the agencies inside the internal actions. So, by the internal actions of neighboring articles, these forces we call as internal forces. And by Newton's third law, that is every action has equal and opposite reaction, these internal forces they occur in pairs. So they must be which are equal and opposite. So what about the sum total of their moments? It becomes 0. So now if L is the sum of moments of the external forces, so the internal force becomes 0. Now we'll see about the external force. Suppose if L is the sum of moments of the external forces about axis, then I theta double dot must be equal to L. And this we call as the fundamental equation of motion of a body about fixed axis. So this equation similar to the equation P is equal to m. Now conservation of angular momentum. And we have seen that I theta double dot is equal to L. So for I theta double dot can be written as d by dt of I theta dot, and that is equal to L. So angular momentum is equal to I theta dot, and that is equal to I omega. We can replace I theta dot by I omega, so that d by dt of I omega is equal to L. So that means that rate of change of angular momentum of rigid body is equal to moment about that axis of the external forces acting on the body. So if L is equal to 0, then d by dt of I omega also becomes 0. That implies I omega is a constant. So if the external forces, moment about the external forces becomes 0, then the angular momentum is a constant. Now, principle of conservation of angular momentum. The algebraic sum of moments of external forces about fixed axis is 0. Then the angular momentum of body about that axis is constant. So we can observe the principle of conservation of angular momentum here. If L is equal to 0, then I omega is equal to constant. So this is called the principle of conservation of angular momentum.
Now we can see an example. A uniform rod of length 2a which stands freely about one end and falls from horizontal position. Show that its angular velocity when it is first vertical is root of 3g by 2a if it hangs vertically and be at rest. To make a complete revolution, what is the angular velocity? And this is the initial position of the rod AB, and G its center of gravity, and M is the mass of the rod. Now initially the rod is at rest, so initial kinetic energy of the rod will be equal to 0, and we know that moment of inertia of a rod at A is equal to 4ma square by 3. Now at the vertical position, the center of gravity changes from the point G to point G1. So the G1 is the position of the center of gravity at the vertical position, and omega is the angular velocity. Now the present kinetic energy will be equal to half I omega square. And if you substitute the value of I, you will get 2ma square omega square by 3. Now the change of kinetic energy will be equal to work done on the rod, and that is equal to present kinetic energy minus 0. That is 0 is the initial kinetic energy. So we'll get 2ma square omega square by 3. Now at the vertical position, the center of gravity of the rod is shifted from G to G1. Also, work done by the weight of the rod is equal to mg into displacement A. So these two are equal. 2ma square omega square by 3 is equal to mga, and omega square is equal to root of 3g by 2a. Now consider the vertical position. So let omega 1 be the new angular velocity, and this velocity, angular velocity of AC will be equal to 0. So now the change in kinetic energy will be equal to 0 minus half I omega 1 square, because here the present kinetic energy will be equal to 0, because it is given that the rod is at rest and it is at vertical position. Therefore, present kinetic energy is equal to 0 and initial kinetic energy is equal to half I omega 1 square. And now the work done will be equal to minus mg into 2a. So here the displacement will be equal to 2a. Now minus half I omega 1 square is equal to minus mg into 2a. So from this you can get the value of 1, and that is equal to root of 3g by 2a. So this is the angular velocity for one complete revolution. Next, compound pendulum. So what is a compound pendulum? A rigid body oscillating freely under gravity about a fixed horizontal axis is called a compound pendulum. If m is the mass of a rigid body and g is the center of gravity, and then we know the expression for moment of inertia, that is equal to mk square, where k is the radius of gyration of the body, and the equation of motion is mk square theta double dot is equal to moment of the weight mg acting at g. Moment of the weight mg is minus mg h sin theta, because it will be considered in the opposite direction. Therefore, we put minus. So minus mg h sin theta, and from this triangle you can observe that sin theta is equal to lg by og, and lg is equal to og sin theta, and that is equal to h sin theta. H is the vertical distance. So this is equal to minus mg into lg. So the reaction at O gives 0 moment also. And if theta is small, we can take sin theta is equal to theta. So now the angular acceleration theta double dot will be equal to minus gh by k square sin theta. That is theta double dot equal to minus gh k square theta. We can replace sin theta by theta because theta is a small value. So theta double dot is equal to minus gh by k square theta, and this is the simple harmonic motion with the period t, where t is equal to 2 pi by root of gh by k square. So this is the general equation of a simple harmonic motion. And also, if a simple pendulum of length L, then L theta double dot will be equal to minus g theta, so that theta double dot will be equal to minus g by L theta. So this is also a simple harmonic equation with the period 2 pi into root of L by g. Now replace L by k square by h. So motion of a compound pendulum is same as that of a simple pendulum of length k square by h. So this we call as a simple equivalent pendulum. So a simple pendulum which oscillates in the same period as the compound pendulum is called the simple equivalent pendulum. Then we show that the center of suspension and the center of oscillation are interchangeable. Suppose O is the center of suspension. So center of suspension is nothing but the point where the axis of rotation meets the plane through center of gravity perpendicular to the axis of rotation. So now you take length OC is equal to k square by h. So this is the length of the simple equivalent pendulum. And here C is the center of oscillation and capital K is the radius of gyration of the body about a parallel axis through G, and small k the radius of gyration about the axis of rotation. By theorem of parallel axis, k square, small k square is equal to capital K square plus h square, where h is the distance OG, that is the distance between the center of suspension and the center of gravity. Then OC is equal to k square by h. So this is equal to capital K square plus h square by h. And also CG is equal to L minus h. Now we are going to change the center of suspension from O to C. So let us see what happens. Now we are changing the center of suspension to C. So let C be the center of suspension and let O1 be the new center of oscillation. Then CO1 is the length of the simple equivalent pendulum about C, and if you take L1 is equal to CO1, then by the similar process L1 is equal to capital K square plus CG square by CG, and this is equal to K square plus L minus H the whole square by L minus H. Also we have K square plus H square by H is equal to L, so that we can get L1 is equal to L minus H into H plus L minus H, and that is equal to L. So we get CO1 is equal to OC. So O and O1 are nothing but the same points. So if we change the center of oscillation, center of suspension from O to C, then the new center of oscillation is the point O. So both are interchangeable.
Next, minimum time of oscillation of a compound pendulum. If T is the period of oscillation of a compound pendulum and L is the length of the simple equivalent pendulum, and we know that T is equal to 2 pi into root of L by G. Now T is minimum if L is minimum, and we know that L is equal to K square by H, where K is the radius of gyration about the axis of rotation and capital K is the radius of gyration about the line through the center of gravity parallel to the axis of rotation, and also K square, small k square is equal to capital K square plus H square. Hence L is equal to capital K square plus H square by H. Now to find the minimum value of T, we will differentiate L with respect to H. So dL by dH is equal to minus K square by H square plus 1. And again differentiate again. So d square L by dH square is equal to 2 K square by H cube. So we get the positive value. If the second derivative is positive, then the value is minimum.
The minimum value can be obtained by equating the first derivative to 0. That is dL by dH is equal to 0. So if you equate this to 0, we will get H is equal to K. So the time of oscillation is minimum when H is equal to K. That is the radius of gyration. And let us see what is torsional vibrations. A uniform cylindrical bar which is suspended by a wire with one end and attached at center C and the other end to the point O. So there is no twist or torsion in equilibrium. We know that in equilibrium position there is no torsion or twist. Now suppose let theta is the angle of twist, then there will be a restoring couple which is proportional to theta. Restoring couple means two forces which are equal and opposite. So there will be two forces acting which are equal and opposite that will restore the position, and that will be proportional to theta. And we take suppose let it be lambda into theta. Now the equation of motion is mk square theta double dot, that is equal to minus lambda theta. We put the negative sign because the couple tries to restore the position. so that we have put minus here. So this is equal to minus lambda into theta. So theta double dot is equal to minus lambda by m k square theta. So this is the general equation of a simple harmonic motion. Therefore, this represents a simple harmonic motion with the period 2 pi into root of m k square by lambda. So you practice all the worked examples and all the best. Thank you.